Hey chemists, how you going? Just want to work through some of the Essentials book questions for subtopic 2.3, which is looking at quantities of molecules. So first of all, we're starting with question 18. So we're looking at calculating the number of molecules in 2 grams of each of the following amino acids. So the first step that you have to do is calculate the number of moles of each of these substances, which is the mass of the substance, so 2 grams, divided by the molar mass of the substance, which is given to you in the questions. So we won't have to figure them out. So if I'm just doing this one in my calculator, 2 divided by 75.07, which is going to be this, okay? Now I've rounded that off in my answers. So I've rounded it off to one significant figure, which is 0.03, so that 3 is significant, and that's because the mass in grams is one significant figure, so we'd always round off to the least precise measurement. However, we are calculating the number of molecules, not the number of moles. So what we're going to do is this equation up here. So the number of molecules, which is big N, is going to be number of moles multiplied by big N with a little a, which means Avogadro's number. Okay, so our second part of this is going to be the number of molecules is equal to the number of moles multiplied by Avogadro's number, which is going to be, now I will write down my rounded off number in here, but I'm going to use the correct number in my calculator. Okay, so multiplied by 6.02 times 10 to the power of 23. Now I'm not quite sure I can do powers in this textbook. No, it doesn't look like I can. So when I'm going to, actually, I'll just make sure I write it like this, to the power of 23. So that is going to be, so multiplied by 6.02 times 10 to the power of 23 is going to be this here. So the number of molecules is going to be 1.60 times 10 to the power of 22 molecules. Okay, so for all of these, I can pretty much do the exact same working out step, and I'm just going to just substitute and change. Okay, so I'm just going to save myself a bit of time here, and I'll just copy paste. And for you, if you're writing it in your book, you'll be essentially doing the same thing, but you'll just be substituting the same numbers. So for this one here, for glutamic acid, the mass is 2 grams because all of these are 2 grams. But when we calculate the number of moles, we're going to change that to 147.13. Okay, so I can go 2 divided by 147.13, which is going to be this here. So I'll round that off to 0.01, which is to one significant figure. However, when I do my equation in the calculator here, I'm going to use that exact number, even though I've rounded it off in my working out step. So then I'll multiply the number of moles by Avogadro's number, 6.02 times 10 to the 23, and I get this many molecules. So that's going to be 8.18 times 10 to the power of 21 molecules. Now you might ask why I'm rounding off there. To be honest, I am not using significant figures for this. I'm just rounding off to something that I think is reasonable. So I'm just going to go to 3 sig figs or 3 decimal places. I just think that seems reasonable for this question. So tryptophan, I'll change the molar mass to what's given. So I'll be going 2 divided by 204.23, which is this. Now this one here is interesting because it's now in scientific notation. So I can write that as 9.8 times 10 to the power of -3. So I can keep it in scientific notation, that's fine. And I'm going to multiply that number by Avogadro's number to go from the number of moles to the number of molecules. So multiply by 6.02 times 10 to the 23. So that is going to be 5.89. I'm going to round that off to 5.90 times 10 to the power of 21 molecules. Awesome. All right, Copy paste again. It's getting a bit redundant now, so we'll go molar mass for valine, 117.15. So I'll go 2 divided by 117.15 is equal to 0.017. So I'll round that off to 0.02 mole. And then multiply that by Avogadro's number to give us the number of molecules. So I'll just go 0.02 and then multiply by Avogadro's number to give us 1.03. So round that up to 1.03 times 10 to the 22. 1.03 times 10 to the 22 molecules. So I won't do the last two because it's the exact same thing, but hopefully that makes sense here. So copper is used to fabricate electrical wire. A length of 50 centimeters of copper wire weighs 7.88 grams. Determine the number of moles present in the length of wire. So that's easy. So that's going to be, we have a length given to us and we've got a mass. The length doesn't matter. That's to throw you. Okay. So the number of moles, the formula is mass divided by molar mass, just like you were using above. So it's going to be 7.88 grams divided by the molar mass of copper. So if I go to my periodic table and find copper, it's here, and the molar mass is 63.546. 63.546. So we'll go 7.88 divided by 63.546. So that's going to be 0.124 mole. Okay. I'm going to round that off to 3 sig figs. Okay. So the 3 significant figures are these 3. And that's because the least precise measurement is also the 3 sig figs. Determine the number of atoms in the wire length. That's easy. The number of atoms is equal to the number of moles, multiply Avogadro's number. So that's going to be 0.124 multiplied by 6.02 times 10 to the power of 23, just like we were doing before. The trick is though, don't put 0.124 back in your calculator. Use the precise measurement here. Okay, so multiply by 6.02 times 10 to the power of 23. Yep, is going to be 7.4647 molecule. Times 10 to the power of 22 molecules of copper. Okay, done. The next one, tartaric acid or cream of tartar, which has the formula here, is a byproduct of wine production left as a residue on the inside of wine barrels. It's commonly used as a leavening agent in baking when combined with baking soda. Carbon dioxide is produced, which expands the dough. Tartaric acid is sold in 125 gram jars. Calculate the molar mass of the cream of tartar in grams per mole. Use the periodic table of elements to determine the molar masses of carbon, hydrogen, and oxygen. So we're going to calculate the molecular mass of C4H6O6. Now it kind of triggers me a little bit that I can't make this subscript. What if I copy paste that if I can do that? No. All right, so you're just going to have to deal with it, okay? So the molar mass is going to be 4 times 12.01. Now that's because there's 4 carbons, okay? So if I go here, carbon, the molar mass is 12.01. That's 12.011 on this periodic table, but I'm used to doing it like this. So I'm just going to do what I normally do, plus 6 hydrogens, which is 1.008. And if I quickly check over to my hydrogen, you can see it's 1.008. Oops. Plus 6 times oxygen, because there's 6 oxygens here, and the molar mass of oxygen is 16, or 15.999 if you're looking at that one, but I've always done it as 16, so I'm just going to do that. So we'll just go 4 times 12.01 plus 6 times 1.008 plus 6 times 16. So that's equal to 150 0.088 grams per mole to the power of -1. Okay. Yep, done. Determine the number of moles of the cream of tartare present in 1 jar of the cream of tartare. Okay, so the number of moles is equal to mass divided by molar mass. And now if you're wondering how I know that, that formula is given to you, okay? So you look it up, look at your notes. You don't have to remember it, but obviously with a bit of practice, you will remember it. So the mass in this instance is the 125 grams because there's that much in a jar. So that's given to you. Divided by the molar mass, which is this. So the number of moles, 125 divided by 150.088. It's going to be slightly less than 1. 0.832. No, 833 mole, which is rounded off to 3 significant figures. How many molecules are present? Same as before. The number of molecules is equal to the number of moles multiplied by Avogadro's number, which is going to be 0.833 times by 6.02 times 10 to the power of 23. So I won't use my rounded off version. I'll use what's in the calculator already. Multiplied by 6.02 times 10 to the power of 23. Gives us 5.01. Yep. Times 10 to the power of 23 molecules. Cool. Done. All right. So next we're going to be looking at percentage composition. Okay. So basically what you want to do here is you're doing a percentage calculation and you're taking the masses of each individual element into account when you do this. All right, so I'll show you how to do it. There are 16 known. Now the formatting for this might not be great with just typing, so I'll try my best. So there are 16 known iron hydroxides and oxyhydroxides, the best known of which is rust, a form of iron oxide, which is known as ferrous oxide. So iron 2 oxide, FeO, is commonly known as ferrous oxide. Determine the percentage composition of iron in the compound of ferrous oxide. So the percentage composition is going to be equal to the molar mass of Fe, because that's what we're trying to figure out, multiplied by the number of atoms of that element. Okay, so I'm just trying to look up here where it says it exactly. The number of atoms in the molecular formula. And that's represented by that N. Okay, so the number of atoms of Fe. Remember how the big N up here was the number of atoms in Avogadro's number, or the number of Avogadro's number? So that it's kind of the same down here. It's the number of atoms in here. Now I'm going to put it in brackets because I can't do all over written like this. Okay, all over the molar mass of FeO. Oops. Yep. Okay. I think that's the best way I can represent it. So the percentage composition is going to be equal to the molar mass of iron. So I look here and I want to find iron, which is here, 55.845. 55.845 times by 1, because there's 1 Fe in FeO, divided by the mass number of FeO. Okay, so that's going to be 55.845 plus 16, because there's 1 iron and there's 1 oxygen. Okay, so that's just calculating the molar mass, just like you've done previously. And then we're going to times all of that by 100. Okay, so let's give that a go in our calculator. So we'll go, we'll go 55.85 divided by I probably didn't need to put that in brackets, but that's okay. 55, oh, whoops, I was supposed to do 845. 45 divided by bracket 55.845 plus 16 times by 100. Yep, so that looks pretty good. So the percentage of Fe in FeO is 77.73%. Now, I'm just doing it to 2 decimal places because that's just generally what you do with percentages, okay? So we'll just leave it like that. So that should be good. That one took a while, that's okay. So let's do the next one. And I'm gonna be cheeky and just copy the formatting just to make it a bit easier on myself here. So what am I gonna change? The percentage composition of iron in the compound Fe2O3. So I'm still doing the mass number of iron and the number of molecule or the number of atoms of iron in the molecule, but the molecule is different now, Fe2O3. So what changes? Iron, the same, the molar mass of iron. It's still 55.845. The number of atoms of iron in this one is now 2 because it's Fe2. So I'll change that to 2. Oops. Now here, the percentage composition, it's going to be 2 times this plus 3 times this, okay? So that's because we've got 2 ions and 3 oxygens in here, okay? So let's do this one. We'll see if this works in the calculator. 55.845 times 2 divided by 2 times, now I should be able to just do this as a run-on sentence, that'll be fine. 55.845 plus 3 times 16 divided by, times by 100. So can you see why it's important to write it down, what you're putting in the calculator, because otherwise you can easily make a mistake. So we get the percentage of Fe in Fe2O3 is 69.94%. Cool. State which iron oxide provides the purest source of iron. So this would be FeO due to a higher percentage composition. So 77.73% versus 69.94% for Fe2O3. So it's always good, even though it's 1 mark, you get it for saying FeO, it's just always good to refer to your numbers. So aspirin is a compound with molecular formula C9H8O4. Determine the percent composition for each element present. Okay, so this one's longer now. How exciting. So what we'll do, we'll go percentage. Now this time, I'm going to be a bit better with my labeling. So I'll say percentage composition of carbon, percentage composition, so I'll do carbon first. So it's going to be carbon and the number of atoms of carbon divided by the molar mass of the whole compound, which is C9H8O4. Okay. So that will get the molar mass of carbon, which is 12.01. We checked that before. Times by how many atoms of carbon? We've got 9. Divided by the molar mass of the whole thing. So that's going to be 9 times 12.01 plus 8 times 1.008, which is the molar mass of hydrogen, plus 4 times by 16, which is the molar mass of oxygen. And then times 100 is always going to be there, okay? So this is going to be the percentage of carbon in the aspirin, okay? So we'll give that one a go. Okay, let's try 12.01 times 9 divided by 9 times 12.01 plus 8 times 1.08 plus 4 times 16, all multiplied by 100. So that gives us 59.99. That's actually rounded up to 60.0%. Okay. Now, I'm just thinking I should be able to go back just to save myself some time, because when I do the next one, so the next one is going to be percentage of hydrogen. So that's going to be the molar mass of hydrogen versus the number of atoms of hydrogen, but the bottom number is the same. So all of this is going to be the same because that's got to do with the formula here. Okay. So this one is going to change to 1.08 multiplied by 8 because there's 8 hydrogens. Now what I can do is just go back in my calculator and just change that first set of numbers. So I don't have to write the whole thing out again, which is handy, saves you a bit of time. So that gives you 4.48%. And then the last one is going to be, I'm mindful that this is just a lot of text here. Oh, whoops. Can I make it bold or something? No. All right, so the last one is the percentage of oxygen. So what are we going to change? We're going to be changing the molar mass of oxygen and the number of atoms of oxygen. So that's going to be 16 and it's going to be 4. So again, I'll just go back in my calculator using my buttons and I'll go over here, delete, 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 delete. We'll do 16 times 4 and that gets 35.53%. For carbon, oxygen. And we'll probably just check that they add up to approximately 100%, and they pretty much do. There's a slight rounding error here, but apart from that, we are golden. Cool, smashed it. All right, the next one is essentially what we've just done, but this time we're going to use ratios in order to determine the empirical formula. So the empirical formula is the lowest or the simplest possible version of the ratio of the atoms. Okay, so the bacterial fermentation of grain to produce ethanol forms a gas with a percent composition of 27.29% carbon and 72.71% oxygen. Determine the empirical formula for the gas. Now, for these types of questions where you get given a percentage but you don't get given a mass, we're going to assume mass is 100 grams. Okay, so in 100 grams, you have 27.29% carbon and 72.71% oxygen. Okay, which makes sense because essentially we're saying that, whoops, just completely stuffed that up, that's okay. So in 100 grams, because the percentages are like this, if we say the mass is 100 grams, then those masses will match up with our percentages, okay? So that's the first assumption that we'll make, and then we can do the calculation from there, all right? So the next thing we're going to calculate is the number of moles. I think you'll find a pattern whenever you're comparing anything to do with chemicals, you have to do the number of moles. It's just that simple. So let's calculate the number of moles of carbon. So that's going to be the mass divided by the molar mass. So the number of moles of carbon is going to be 27.29 grams divided by the molar mass of carbon, which, as we hopefully remember by now, is 12.01. So 27.29 divided by 12.01 is 2.27. 2.27 mole. And then we'll go the number of moles, and we should do it over this side of the page. I tried to use my hand then, that wouldn't make sense. But I'll do it underneath just because that's how my working out space is going to work. And I'll just cheat again and copy paste, except this time I'm doing oxygen. So the formula is going to be the same, but all of the numbers are going to be different. So we're going to do 72.71 divided by 16. So the number of moles of oxygen is going to be 72.71 divided by 16. So that's going to be 4.54. So now we're going to do the empirical formula, okay? So what we'll do now is we're going to divide both of these values by the smallest mole value, okay? So the number of moles of carbon is going to be 2.27 divided by 2.27. And the number of moles of oxygen is going to be 4.54 divided by 2.27. So that is going to equal 1, and this is going to equal 2. So 4.54 divided by 2.27 is going to be 2. Okay, so that's my ratio. All right, so the ratio is there are 2 moles of oxygen for every 1 mole of carbon. Okay, now in reality, it's not 2 and 1, it's 4 and 2. Okay, but we're just going to scale it down by dividing by the lowest mole value to get a ratio. So we're scaling down to these small values that are essentially, you have 1 and then you have a comparison to 1. So we can say, therefore, the empirical formula is CO2. Okay, CO2. Now I know, based on my knowledge of this reaction, that that is also the molecular formula. The molecular formula is the real formula. Okay, the empirical formula is in simplest form. Okay, so you could potentially scale that up. So you could have C2O4, C3H06, C4O8, and so on. Okay, but the empirical formula is the simplest formula. Okay, if you look up here, and I know this is a lot of text, but it has it side by side, the comparison. So you've got it side by side and then you divide like this. I like that formatting better than what I've done, but I'm limited to what I can type in here. Okay, so the empirical formula is CO2. So a second one, we've got all these percentages again. So we assume mass, I'm not even going to read it because I know it's the same type of question. So we assume the mass is 100 grams. So the nicotine contains 74.02 grams carbon, 8.710 grams hydrogen, 17.27 grams nitrogen. So then I'm going to be doing the number of moles and comparing all three. Okay, so the number of moles of the carbon is going to be mass divided by molar mass. So that's going to be 74.02 grams divided by 12.01. So the number of moles of carbon is going to be 74.02 divided by 12.01 is 6.16 mole. So I will go, the number of moles of hydrogen is mass divided by molar mass. So 1.008 mass first, molar mass second. So mass is going to be 8.710, so 8.71. So 8.71 divided by 1.008 is 8.64. And then the number of moles of nitrogen is going to be the 17.27 grams divided by the molar mass of nitrogen. So let's go have a look. Nitrogen 14.007. I've always done 14.01, so I'm just going to do that. Set in my ways. So that's 1.23. Okay. So then we're going to be doing the number of moles of carbon, number of moles of hydrogen, number of moles of nitrogen. So we're going to do 6.16. Now what's the lowest number? It's 1.23. Okay. So we're doing our ratios now. 8.64 divided by 1.23. So you divide all of them by the lowest number. Okay. And the purpose of that is going to be bringing the lowest one to 1, and everything else is going to be compared to 1. So 6.16 divided by 1.23 is going to be close to 5. And then 8.64 divided by 1.23 is going to be close to 7. So the empirical formula is going to be C5H7N. Okay, so 5 to 7 to 1, carbon to hydrogen to nitrogen. The last bit is, oh, actually, no, there's a few more. So now we're going to do the same thing, the empirical formula, except this time we are given the mass of the compound instead of a percentage, okay? So up here we had percentages. This time we have masses, okay? We get given masses. Is that going to be harder or easier? Now, in reality, it's just going to be easier because up here we had to assume mass is 100 grams and then convert it to grams by, it's the same number, but just kind of write that extra line. This time we don't have to do that. We just have to go using masses. So it's the exact same thing. So if we want the number of moles, and again, I'm barely reading the question here. If I want the number of moles of iron, which is Fe, it's going to be mass divided by molar mass, which is going to be 69.94 grams divided by the molar mass of iron, which is 55.845. .94 divided by 55.845. So 1.25. And then we've got the number of moles of oxygen, which is equal to mass divided by molar mass. Moles of oxygen is 30.06 divided by 16. Oops, I didn't write that here. 6 divided by 16. So that's 1.88. So then the number of moles of Fe equals 1.25 divided by 1.25, which is equal to 1. So we're just scaling down based on our ratios. Oops. Moles of O is equal to 1.88 divided by 1.25. Now this is where we're going to run into a bit of a challenge. So it's 1.5. Okay. Now you can't have 1.5. So we're going to scale that up. By multiplying by 2. So we want to get the lowest whole number. Okay. So the number of moles of Fe is now going to be 2, and the number of moles of O is now going to be 3. Okay. So hopefully that makes sense, because you can't have half in a formula. So you have to have the lowest whole number, and they need to be scaled appropriately. So if I multiply both by 2, then it's going to scale up to 2 and 3. So it's going to be Fe2O3 is the empirical formula. That is it. If you lasted that whole 35 minutes, well done. But the bonus is we've done every single question in that subtopic in that chapter. So we are absolutely golden for any questions in the assessment based on this. So thanks for watching. Hopefully you learnt something, and good luck with the practice for your assessment. See you later.